So welcome to the multi-objective optimization lecture. Now, my suspicion is that prior to seeing these slides, you probably never heard of the term multi-objective optimization. It is a term that's not used in economics. However, the basic concepts, for example, the Pareto frontier, are well known to economists. However, it's not in, I don't know of any previous work in economics which made critical use of the multi-objective optimization ideas. And that's what we're doing here today. Now, by the way, the slides are obviously, it is joint work with Philip. You'll be able to tell which slides are Philip's and which ones are mine. That's always obvious. This also will cover some joint work with Carlos Rangel, and who's a graduate student at Penn State, and also Juan Ricardo O, who's a graduate student finishing up here at Stanford. And I met both of them through a former student of mine who is a professor at El Colegio in Mexico City. Let's begin. Okay, let's. Yeah, so those slides should display. The slides should be displayed on your screen now. Now, multi-objective optimization, and of course, we're going to have a focus on a particular kind of optimization problem we see in economics, and that's optimal taxation. Now, the motivation is a cute little picture here. That guy actually looks to be too young to really be threatened by taxes, but anyway, it's a cute picture. Now, see, what's the motivation for this is that in choosing taxation policy, the planner has multiple objectives, hence the term multi-objective. Now, the planner has to take into consideration the revenue of the taxes, the utility of the taxpayers, their happiness. He may also care about the impact on distribution. Now, he may also care about the utility of particular important people. Like, for example, that certainly was a feature of the CARES Act, that important people got lots of money. Now, by the way, this kind of problem is not unique at all to economics. In fact, there's a large literature in the computational engineering field, I guess you'd call it, where you talk about problems in other contexts, such as airplane design, which face the same things, same trade-offs. There's a trade-off in designing an airplane. You have a trade-off between fuel efficiency, carbon emissions, sound is a critical one because many airports are located close to densely populated areas. So those people don't like noisy planes. You have the operating cost considerations of how much you have to spend on pilots. For example, many planes used to have 3 people in the cockpit. Now many are down to 2. So there's many features that go into choosing an airplane design, and there's trade-offs. There are always trade-offs. And so this is another example of multi-objective optimization, because of course the firm designing the airplane wants to maximize profits, but then he also has these other considerations to keep in mind. Now, here's what we call the Pareto frontier in economics. Now, suppose you have 2 goods and services. Those are 2 kinds of goods. And a Pareto efficient So this is a representative of the production possibility frontier, let's say. These are the combinations of goods and services which are feasible for an economy to produce. And so points A, B, and C are all Pareto efficient points, because in order to get more of services, if you're at A, you want more services, you have to give up some goods. Now, Pareto, the point D is Pareto inefficient, because you can make everybody off by choosing A instead of D. So it's an inefficient point, because both of your objectives, goods and services, will be higher at A than D. And that's the key thing here, is that you have a point here in two-dimensional space, and Pareto inefficient points are those that are dominated on all dimensions. Now, here's an example from somewhere, and anyway, in the optimization, multi-objective optimization literature, and you can see why it's a cute example. Suppose you have two objectives, F1, and the objective is a function of n xi's, or n minus 1 xi's, n xi's, and that one objective, the value of one objective is this ugly thing, and the other objective is this slightly less ugly thing. Now, the Pareto frontier here is not going to be a nice, smooth line. We're used to Pareto frontiers in economics, which are nice, and they're convex sets with concave frontiers. That's not the case in general. That's not even the case in general in economics. And here's a case where, now we have to keep in mind here a couple of details here. The planner, which has these two objectives, is choosing n values for x, n xi's. There's x1, x2, x3, up to x10. So there's a 10-dimensional range of choices. However, there's just two objectives that that this problem cares about. Now, what this Pareto frontier does is it shows you somehow, we'll talk later about how, using this, you can find the Pareto frontier. And then now, once you have the frontier, then suppose you want to find the point that maximizes F2, but subject to F1 being bigger than some critical value. Well, all you have to do then is just go through the Pareto frontier, and then you take a slice at the F1 minimum value, and there you have the Pareto point. It says that the best F2 conditional on this constraint in F1 is at this point. Now then, that point, so like if you're doing a computer program, then that point, you then would say, well, how did I get that point? And so your computer would have kept a record of what combination of 10 x's will give you that point. So you have to keep in mind here all the time that there's the payoff space, which here is multidimensional, in these pictures just two. And then there's the policy choice space, which here is 10. So we're going to be, in thinking about this, you have to remember that you're bouncing between two spaces, essentially. There's the criterion space, the multiple objectives, and then there's the space of choices. Now, but what we would say, this is, and for example, the x vectors would be an example of what's called a design point. So now one design point dominates some other design point if, oh boy, okay, this goes back to the fact that in engineering, you always want to there's always stated to minimize something. So now the objective, so Y1 dominates the design point Y2 if F1, if objective I at Y1 is less than objective I at Y2 for all I. So this is case where we're trying to do is minimize a minimum problem. Now in economics, we want to maximize, and so this inequality would be reversed. This is the problem with you read this engineering literature and then you forget you got to switch inequalities many times. So anyway, so that's domination. Basically, one point dominates another if and only if it's better in all dimensions. So A, Pareto dominates D because it is better in both dimensions. So now a design point Y1 is Pareto optimal if there is no feasible design point Y2 that dominates Y1. And the Pareto frontier is a set of Pareto optimal points. And so back here, there's nothing that dominates A, nothing that dominates B, nothing that dominates C. No. Now, you have to remember now, though, that domination is a partial order. It's not a complete order. So neither A nor B dominates the other. Neither A or B dominates C. So we're used to, if you're just doing maximizing one objective, all you care about is making that objective higher. But here we have multiple objectives. And so the points here on the Pareto frontier are the set of undominated points. Now, so if we just had one dimension, if this was just profit in the horizontal dimension, then the undominated point would be the profit maximizing point. But no, we have multiple objectives. And so the key concept here is not optimality. The key concept is domination. What's the set of points that are not dominated? That's a Pareto frontier. So what this says is that an efficient choice should be on the Pareto frontier. Now, what choice you make depends on other considerations. For example, if this is your production possibilities frontier and then we had a indifference curve, well, then we would choose a point that where there's a tangency between the two. So this just basically tells someone, so what are the set of efficient points? And in order to choose one, you have to bring in more information. You have to elaborate more on the objective. Now, in the tax problem, here's the trade-off that one faces. You have the utility versus the revenue. Now, revenue is just dollars. That's how much money you raise by the taxes. Now, utility, the utility scale here could be thought of as the utility of the representative agent. Now, if you have multiple dimensional agents, then that differ in some regard, well, then this utility would be some social utility function, which could be a weighted sum of individual utilities. So it's some criteria, it's a criteria related to the utility of the individual agents. Now, by the way, this is a two-dimensional problem. One could imagine where you have revenue, but then you have more dimensions. For example, you might care about the utility of the poor people, utility of the middle class, utility of the rich. And so that would, instead of having two dimensions, you'd have four dimensions. Actually, in this case, it'd be easy to add graphically utility of the poor and then utility of the non-poor. That would give you that kind of trade-off, which is important in many political contexts. So this is the Pareto frontier in tax problems. And for basic tax problems, we have representative agents or some utilitarian objective. Now, by the way, this is written as a concave frontier. That is not always, there's no reason to think that the frontier is concave. Now, unfortunately, the examples we found are too simple, but they tend to have concave frontiers. There's no reason for that being the case, and I'm sure we'll find concave frontiers when we go to more complex tax problems. Now, by the way, here's a case of where the frontier is not even a continuous curve. It's piecewise continuous, but then you have these breaks where what's happening is that one of the objectives, it must have some hill, must have multiple hills. And so as you change the payoff from the other objective, you change where the top of the hill you're going to. So discontinuities are also natural. Notice, however, that even in this ugly one, it looks like these are piecewise continuous. And I think in many of our economics examples, we could expect this frontier to be piecewise continuous, hopefully even differentiable. But the Pareto frontier does not need to look like this. This is, okay. Now, how would we form it? Now, what we're going to do is an example. So I'm going to lay down a specific example of optimal taxation and then go through sort of the four methods that I and my collaborators have used. So what we're doing here is we're doing a life cycle model with taxation. So you have a government, now you have the agent, the representative agent that has lifetime utility from age 1 to age cap T, and that is going to be a function of the utility as well as the tax parameter. Maybe the tax parameter affects utility directly. So there's the present value of utility, and then the present value of revenue, where revenue is a function of the tax scheme, as well as the choices of assets, consumption, and labor supply. Now, we're all familiar with this. Government wants to maximize utility subject to a revenue constraint. However, the way that we conventionally model this in economics is to add incentive compatibility conditions to this. So basically what you have is the government maximizes utility subject to revenue being above some target, but also the government makes direct choices of C and T and assets, but then that's subject to incentive compatibility. Now, so this so you've seen that kind of problem before. And we're going to do representative agent. Now, we're going to look at it in a way, this problem in a way that's somewhat different than the usual way you've seen optimal taxation problems written. So what we do is we focus on the policy variable, the tax parameter, the tax schedule, which could be a vector of things. In this case, it's just going to be a tax on consumption. There's going to be a variety of choices here. Consumption taxes, labor taxes, interest taxes, etc. So there's a vector of these things. Now, if the agent, so the consumer, faces a tax schedule tau, so you can think of this like a game where the government declares tau and then the consumers make their choices. Now, the consumer's choices will be represented as will be the solution to this optimization problem. You maximize present value of utilities subject to the budget constraint. And this is just the budget constraint that AT is the assets at the beginning of a period. And then these are these constraints. When you die, you have to have, you can't die until you paid off all your debts. I believe I've also buried in here. I also assume that you're initially born with nothing. And so then you choose your consumption and labor supply and your savings. And then of course there's in each period, there's a tax bill that you have to pay, which is a function of your choices in that period, as well as the tax parameter. And then of course, for any sort of tax formula, there's also a revenue function. And so given any tau, then the revenue, and we're going to call that F sub 2, keeping in the notation of our well, there should be an F sub 1 up here, is the revenue of tau, where revenue is the present value of the revenue collected each period, where the A, C, L vectors are the solutions to the agent's problem. So if I want to be really pedantic to this, I would say A sub t is a function of tau, C sub t is a function of tau, L sub t is a function of tau, that function being given up here. So now we have the utility of the agent and the revenue of the government, both expressed as functions of the tax schedule tau. Now, what we then can do is we can think of the optimal tax problem as basically finding the optimal tax, the optimal tau, the optimal tax schedule, such that it maximizes utility, but the revenue hits some target revenue R star. That is how you conventionally see these tax problems written, is that you maximize utility subject to incentive compatibility conditions and revenue constraint. Now, you might wonder, where are the incentive compatibility conditions? I mean, one of the first times I presented this, somebody said, well, where's the incentive compatibility conditions? Well, they're already buried in this U of tau function. Because given a tau, every agent has made the optimal choice. And so therefore, the choice of consumption, labor, assets, et cetera, has to be incentive compatible. They've made the choice. So all of the incentive compatibility conditions are buried inside this function U of tau. So the incentive compatibility conditions are there, but they're just buried in the computation of U of tau. Now, this problem is normally really difficult. Outside of some very simple cases, the utility function is generally not going to be a nice concave function of the tau vector, and revenue is not going to be a nice function of the tau vector. In fact, the revenue function can easily be a discontinuous function of the tax parameters. So this is, if you write it down in this fashion, or write it down in this way, plus incentive compatibility conditions. By the way, the thing is, if you wrote it down in the conventional fashion, your utility term would be your conventional utility function. That's going to be nice and concave. But then all the nasty stuff is in the constraints. And so your constraints that need not be convex, it need not even be connected, it's ugly. It's awful. And if you try to solve one of these problems using, let's say, a standard optimizer, you could end up in a deep trouble. Outside of some simple problems, the standard software can't handle these problems because of the non-convexities in the tax schedule, various things. So that solving one of these problems is very difficult, typically, and beyond the ability of most, even the most advanced solvers. Many years ago, there's a grant that I was principal investigator on, and part of the money went for having an intern go to Argonne National Labs, and I wanted the intern to work on this problem. But the intern was going to be going to Argonne National Labs, and so he was under the supervision of some computational mathematicians. And so they insisted that he approach this problem in the conventional fashion, writing down a utility function and then revenue constraint, but also incentive compatibility constraints. I told them that it's not going to work. I have a better idea. They said, no, these guys were very good at theory. They were sure that their theoretical methods could work. Well, the summer went by and the intern produced nothing because the constrained optimization problem is really nasty, very nasty. Solving one of these problems is very difficult. So instead, what we're going to do is solve a continuum of these problems. Now, there are many, because what I'm going to do is I'm going to say, okay, solving one of these things is hard. Oh, gee, it is hard. It is awful. Multiple local min. Also, all sorts of nasty stuff can happen. Non-convergence. But I'm going to solve a continuum of them because I'm going to solve out for the Pareto frontier. And once I've solved out for the Pareto frontier, all I need to do is that once I have that, and if I want to find what's the best thing if the target revenue is 40, I just find that point right there, which is, and then look at computer memory to see what the tax policy was that got us to that point. So solving one of these tax problems is hideous and difficult. Solving a continuum of them, because I could look at all various policies, various revenue. Solving a continuum is easy. Sounds like magic. No, it's not magic. It's just knowing how to use a computer efficiently. Now, so the first, my first work in this was many years ago with Carlos Rangel, and actually first with Juan Ricardo O, who's finishing up at Stanford this year, and then a couple of years later, Carlos Rangel, who is now at Penn State. The first approach is brute force. What you do is you just collect a sample of points in policy space, and then you collect utility and you compute utility and revenue for each of those points. And then you collect the points, and then you sort out the Pareto dominated points. So this is brute force. But the computation here is easy because given the tax schedule, solving for the agent's problem is typically easy, far easier than an optimal tax problem in any case. But solving, given a tax schedule, solving for the agent's problem is easy. And then once you have the agent's choices, recording the revenue is also easy. Furthermore, this is all naturally parallelizable. You could pick a very large set, you could pick a very large sample of points tau in policy space. And then if you have multiple processors, you could have this different processors work on different subsets of the sample. And in no time at all, you could easily have analyze many points in policy space. Actually, what you're going to see today, because the example is simple, is only, I think, I don't know, 20, 40,000 point policies we look at. There are some other applications of this where this was with some other people where I was looking at this, we had billions of points. But because it's naturally parallelizable, you can quickly relatively easily gather up the data. Basically, what is revenue and what is utility at each tau? You generate that using massive parallelism. You collect those points, and then sweeping out the Pareto dominated ones is easy. It's just it's kind of a sorting problem. It's not that, it's easy. And in fact, if you have an enormous data set, there's some fancy method called Dijkstra method for taking a large set of points and then sweeping through finding the Pareto dominated ones. So even if there's a billion of these points, this is a piece of cake. So now another approach, which we refer to as crawling, is you pick some tau in policy space, and you compute the tau utility and revenue for that tau and also for some of its neighbors. So tau and some of its neighbors. And then you find amongst the neighbors some point that Pareto dominates tau. And that gives you a new tau. And so you just keep crawling through parameter space that way. You pick a tau, you see if there's a neighbor that Pareto dominates it, and then you go to it, and then you continue on. So you're crawling. And then, of course, when do you stop? Well, when you stop when you're at a point which has no neighbor that dominates it. Again, this is naturally parallelizable. And then you delete the Pareto dominated points. Now, by the way, stopping here you will stop when you get to a point that is locally Pareto efficient. Locally Pareto efficient. It may not be globally Pareto efficient, but because it's basically, it's saying, oh, I'm at a point where none of its neighbors Pareto dominates it. Okay, that's a local thing. Now, the last step where you where you collect all the points you have, and then you delete the Pareto dominated points, well, if you just got a local solution in this crawling, well, then that gets wiped out in the step where you delete the Pareto dominated points. So this is a case of where, yeah, your stopping rule is basically just a local stopping rule, and there may be multiple locally Pareto efficient points, but then you collect them with ones that are better, and they disappear. So the crawling is another one. And notice, by the way, brute force and crawling makes no assumptions about the smoothness of the problem. Now, what we did, Carlos and Ricardo and I did, we looked at the simple life cycle problem. Gamma is the inverse of the intertemporal elasticity of substitution. Eta is the elasticity of labor supply. And so here we recorded the Pareto frontier. Now notice that on the Pareto frontier, the labor tax keeps going up, up, up. The capital tax, the tax on interest, is basically usually just zero. See, what I did is I said, suppose that I picked, I knew the minimum revenue, knew the maximum revenue, and I picked a bunch of revenues in between, and I said, okay, given revenue target 6.211, what point has the highest utility subject to meeting that revenue? And I got out this point. And then I got out this one for another revenue target. By the way, the increments that I allowed were 0.01 in the tax schedule. Now, so what do we learn from this? What we learned from this is that taxing interest income doesn't seem like a very good idea. And same thing with this example here. When gamma is 3 and eta is 1, capital tax disappears, and as well as with eta equals 3. So the lesson of this seems to be that, well, this capital taxation stuff isn't maybe such a good idea. Now, here is a plot of the entire set of points that I examined. I believe the size of this was 75 by 75, which is a bit over 50,000 points. And so then what I did is, this is a scatter plot of every point, and it has the trade-off between consumer utility and total tax revenue. And then each point here, the color on this side, this graph tells you what the capital income tax rate was at that point. And here it's the labor tax rate. Now, notice that the labor tax rate looks like what you think. Look at the Pareto frontier. Basically, as revenue increases, the labor tax rate gets higher and higher, and which is signified by the redness. Now, however, with the capital tax, it looks like at every Pareto efficient point, the capital tax is 0 or close to 0. Remember the color scale here. And basically, significant capital taxes of any sort kicks you inside the frontier. So this is an example of a visualization. I think of this as visualization as far more informative than that. Who wants to look at this? But this, you get your computer to generate this, and instantly you see the pattern. Instantly you see that the Pareto frontier involves increasing labor income taxation, but basically generally does not involve any significant taxation on interest income. So now, yes, maybe some of these points have a tax rate of 3% or 4%, but again, that there's a lumpiness in this problem. But this picture kind of, with the color scheme, kind of gets rid of that lumpiness and gives you what really is the economics message. This was gamma equals a half and eta equals 1, and barring limit, you can borrow. See, some of these models allow people to see, young people tend to have small income relative to their future income, and so they would like to borrow. And sometimes we let them, in some models, we let them borrow, sometimes we don't. I remember a time when I was I and Glenn Hubbard were presenting a paper at the Brookings Macro Festival that they have twice a year. And we were talking about the impact of borrowing constraints on various macro issues. And we were using an overlapping generations model. And so we were talking about the importance of that constraint when you're young. There's a constraint, you can't borrow against future income. One of our discussants was Bob Hall, who then made many references to the family capital market, and saying that those constraints were not important. Well, why would he say that? Well, you see, Glenn and I came from rather humble backgrounds. Glenn's parents were teachers in Florida, and my father was a farmer. And so when we went to college, there wasn't much of and soon after that, there wasn't much of a family capital market for us. Because in both cases, everybody knew that we were going to be making a lot more money than our parents. And so it's kind of like, why would we, anyway, they had lots to do with their own money, but letting us borrow against our future high income, well, it just doesn't seem right. Bob Hall, on the other hand, his father was a doctor at Stanford University Hospital, and then went down to UCLA Hospital to start up some part of their hospital. And so Bob Hall spent his life bouncing between Palo Alto, Brentwood, a suburb of LA, and then someplace out east for a while when he went to MIT, and then back to Palo Alto. Now, people in those backgrounds, they have family capital markets. Glenn and I didn't. So that's why we're going to look at, this is kind of like the Bob Hall situation. Yeah, do you tax his capital income and labor income? No, you don't tax Bob's capital income. He'll be happy to hear that. Now then, as you change the utility parameters, but keep the borrowing unlimited, borrowing limit is the borrowing limit is 1,000. This should be the asset limit. The assets have to be above negative 1,000. Anyway, so this is, sorry for the sign confusion. So basically we want to test robustness now. This was one pair of utility functions. Now let's look at this. Gamma equals 1/2, eta equals 3. Gamma equals 3, eta equals 1. Now basically, when gamma is 1/2, you get the same result, no matter what eta is. When gamma is 3, then things get a little less clear, but it still is clear that down, boy, capital income taxation, even at the highest revenues, is not going to be much. You're going to be dominated by, you're going to have much more revenue from labor tax. And then here, gamma equals 3, eta equals 3. it still is a case that on the Pareto frontier, capital income, tax and capital income is not a good idea. I think there's other examples. If I jack up gamma to 8, then we get a mixture. Because basically what happens when gamma equals 8, the intertemporal elasticity of substitution is very small. And so taxing capital income doesn't have much of a distortion. So, but notice with this visualization, we see the nature of the Pareto frontier and which are good tax policies, which are bad. Notice that even if we had suppose we had half a dozen different tax schemes, each one could be illustrated by this picture. You could have tax number 1, tax number 2, and there may be some taxes which will always look like capital tax that giving them a positive value never is on the Pareto frontier. So this is a way of looking at just examining the problem and testing robustness. Now, here we say you don't borrow. So this is now Glenn and me. We couldn't borrow against future income. So we had to live off of our earnings during the summertime. And then after we got out of college, we went to graduate school, we had to live off of whatever we had then. Now notice that what happens for small gamma goes a half. Capital taxing is still not a good source of revenue. Now though, when the intertemporal elasticity substitution is smaller, gamma equals 3. People also call gamma risk aversion, but that's a bad, but anyway, that's what they call it. It's really, I should express this in terms of the intertemporal elasticity of substitution, which here is 1/3. And now the thing is that since the intertemporal elasticities of substitution are much lower than then capital tax is not going to distort things so much. And then the capital income tax might be useful. And so here we see the picture. Now the thing is, these tables, who else will look at the tables? Here's the picture. The picture now, borrowing limit is 0 here. And for gamma equals a half, we get basically the same pictures, no capital tax income. But now when gamma equals 1/3, or intertemporal elasticity is 1/3, we see that there are some, if this was finer resolution, we'd see that there would be some red points on the frontier. And particularly, here, yes. There are some red points on the frontier indicating positive capital tax. So here, when intertemporal elasticity of substitution is low, and when the labor supply elasticity is high, then yeah, you want to go towards, you want to use capital income tax. Now remember, the borrowing limit here is important, because even when you could borrow, there's a little tax detail here that's important. See, if you hold assets and then you have interest income, you get taxed on the interest income. However, if you borrow money and pay taxes on your pay interest on your debt, you don't get to deduct that interest on your taxes. That, at least not in the United States today. So even there, it's not a perfectly straight, simple problem. But anyway, you see the tax borrowing limits are going to matter. Now with Philip, the idea is to take advantage of local smoothness, because by the way, slight changes in these tax rates will generically only slightly change the decisions of the agent. So what we want to do is take advantage of local smoothness. So you pick an initial guess, and then we'll go through the details of this, but you find some direction. You use the gradients to find some direction which you can go, which improves all objectives. And then you go in that direction until, as long as you can keep improving both objectives. And then you stop. And so in that direction, you can't find a Pareto improvement point. But then you recompute your gradients. You see if there's a direction in which you can improve everything. And then you keep doing that until there's no possible local improvement. Again, you can start with many, many initial points. It's naturally parallelizable. Now, another idea that Philip is working on the coding for is, suppose the problem is sufficiently smooth, then what you could do is, and I'll even go back to the picture, the ugly one. Yeah, even the ugly picture. Oops, something didn't, anyway, this didn't go well. Yeah, it's fine. I'll delete that stuff. So even back in this one, even back in this one where it's discontinuous, it appears that things move maybe smoothly through this. So the idea is to first use some method, crawling or the gradient business, to find some point on the Pareto frontier, and then use homotopy path following methods to go down and trace out this boundary. Now, of course, you're going to come to a point like this where things don't work out so well. But again, what you can do is start at many different points, and then you trace out from there. And again, that's all very parallelizable. And so you can get the smooth pieces of the Pareto frontier, if not all of them. Now, again, naturally parallelizable. Now I'm going to get into the more formal discussion of how one, I see the brute force stuff I showed you, and then the crawling business. Those are simple ideas, and if you've got and a simple problem, you can do that, and I was able to do that. By the way, I think the data for those graphs took something like 10 minutes for those graphs you saw for the life cycle problem. And I'm sure I can get that down to 2 minutes if I had faster software. I'm just too lazy to write it up in a faster manner. By the way, though, in doing these, in generating the data for this, I did use parallelism on my iMac. This is done using Mathematica. I used parallelism, and so this was done with 12 cores. So yeah, again, parallelism. Now, suppose that you have a problem. By the way, now this is now notation. Multi-objective problems are, the notation for them is this. You minimize y, and then here is a list of objectives. And then here are your constraints. So a multi-objective problem is expressed in this fashion. Minimize y, minimize this vector of constraints over y, subject to y being feasible. So at first, when you see this thing, what do you mean? Well, which one do you want to minimize? Well, this notation tells you you are in multi-objective optimization world. And then the constraint set is, if the feasible set is a subset of Euclidean space, then you're going to have inequality constraints. Typically, this feasible set is also going to have some dimensions in which it's an integer choice. These problems can get to be very ugly in terms of now, suppose that we want to solve this problem. Suppose we want to solve problem 1. Oh, no, sorry. No, this is motivation. Suppose we're back in unconstrained optimization where you have a function of n variables and you have a scalar output. Now, remember what the steepest descent method was. At your current guess xi, you calculate the steepest descent direction. And that is, by the way, this is we're minimizing. So the steepest descent direction is negative of the gradient divided by the norm of the gradient. So this vector is going to have unit length, and it represents a direction. And then what you do is you search in that direction to find some lambda that minimizes the set of points in that direction, which is xi plus lambda times d. So d is a direction, and then this is then in that direction you have a one-dimensional optimization problem over lambda. And then in that case, what you do is when you stop, you update your point, you get your new guess, and then you restart, and you keep going until the gradient of the objective function is 0. Now, in the multi-objective optimization literature, we can follow the same principle. We can use the same idea. We repeatedly search in good directions until we can't proceed. Now, here the notion of good directions has to be refined because we have multiple objectives. So the good direction now, if you're at a point, is the common descent direction omega. Now, omega is some direction in which all of the objectives are improving. In this case, we're doing minimization. So all the objectives are falling as we go in that direction from some base point. So we're at some point y I. We find some common descent direction omega, and then we keep searching over in this direction, keep increasing lambda, and we keep doing that as long as all the objectives are falling. And once we hit some lambda such that one of the objectives is no longer falling, then we stop, and that's our new point. And then from there, we compute a new steepest descent direction and then continue. This is the same as a 1D case, but now we need to calculate a common descent direction now. The common descent direction is first we need to compute the gradients of each. So let ui be the gradient of the ith objective at a point y. So that's a gradient at one of the objectives at y. Now, by the way, you can compute gradients by finite differences, or better now with Casati or some automatic differentiation software. Now, starting from some design yi, what you do is you find a non-zero descent direction vector, omega, which improves at least one objective while not worsening the others. Okay, that's what our goal is. Now, there are often many possible directions to go, and the set of descent directions is actually what we call a convex cone, because it's a convex cone because it's a cone because you're looking at directions and basically infinite length vectors, and it's convex because if you have two vectors that for which all the objectives descend, then any convex combination will also be a descent direction. What we're going to do is choose that one with the minimal norm. So basically, we have the individual gradients. We're going to choose some convex combination. By the way, convex combination means that the alpha i's have to be non-negative, and weights have to add up to 1. And then and we want to find the minimal such the minimal length, minimal norm such direction. And now, by the way, we have to keep track of some things. Now, the set of descent directions is a property of the geometry of the problem, or the basics of the problem. However, when we've introduced a norm, it's now the case that the units will come into play. Depends on how you measure utility or revenue. Is revenue measured in dollars or in billions of dollars? So what you want to do is to change units so that this works well. That's a very vague thing, but you get the point that changing the units can help. Now, for two objectives, we have a closed form solution to that problem. The minimal norm common descent direction is this convex combination of U1 and U2. And here's a formula for alpha. Now, so much for formulas. Here's what it looks like. Suppose you have these two vectors, U1 and U2. Well, omega here is a convex combination of U1 and U2. And it has, of all the convex combinations of the two, it has minimal norm. So that's a good choice. Here with this U1, U2, again, it's minimal norm. Well, how do we know it's minimal norm? Because what you do is you take the line that connects the heads of these two arrows, and then the minimal norm convex combination is going to be perpendicular to that line. Now, sometimes the minimal norm, just looking at the minimal norm solution, is not a good idea. Here you see if you took these as U1 and U2 directions, then the weighted combination that has minimal norm is over here. That's not a good idea. It's not in the convex cone. So then we just set omega equal to one of these vectors, whichever one is closest. So that's how you choose this. Now, in higher dimensions, it gets uglier. You have to solve some constrained optimization problem. That's a tiny one. Now, so a design point is Pareto stationary if and only if the only common direction omega is 0. Now, what does this mean graphically? Well, it means suppose that you're at a point, some policy, and the U2 vector says to go left, to go right, the U1 direct vector says to go left. Well, what the convex cone of this is nothing but the 0 point. And so basically, there's no way that you can, intuitively, it's obvious, there's no way you can improve both, because it says that changing any change in that improves one criterion is going to make the other one worse. Now, so then Philip coded this up, and this is what he got for the Pareto frontier. Now, by the way, we are going to have 3 taxes. And now we see the value. You see, the brute force method was good for handling 2 taxes, labor income and capital income tax. Now, when we go to 3 taxes, well, we could still do it by brute force, but the sampling problem gets worse and worse. But now with this basically smooth the gradient descent direction, we can go much faster and you go to higher dimensional space. And here, the trade-off between utility and revenue does happen to be concave. And I'm sure we'll find uglier ones. Now, what's the marginal excess burden? Marginal excess burden says, so the marginal excess burden is, actually this, maybe this isn't quite, no. Marginal excess burden tells you what is the utility cost of having an extra $1 of revenue. So as you go down this line, you basically the slope of this line tells you what the marginal excess burden is of a tax. And so you see what happens is that it's not so bad, and then it gets really bad here when you have, and by the way, this is marginal excess burden as you move along the Pareto frontier. It isn't saying which tax you're using as you move, but it just tells you what the relationship is between the optimal point that raises this amount of revenue and the optimal point that raises a similar amount of revenue. Turns out that capital income tax is always 0. Now, one reason why we get a more decisive result here is that the brute force method and the crawling method discretize policy space. This is just moving smoothly through policy space, so we're not going to get that lumpiness. And then what we're going to find, what about labor income tax and capital income tax, consumption tax? Well, what we find is that you can't pin either one of them down. And this is the other beauty of the multi-objective optimization approach, is that you can argue all you want over should you tax wages, should you tax consumption. It turns out that it doesn't much matter, because once you're into revenue streams of like 30, you could do it with this range of labor taxes or this range of consumption taxes. My suspicion is that at 30, if you're at this point where labor income tax is 0, then that means that at that point, the consumption tax is high. So basically, we haven't quite worked out the presentation, but I'm sure we could visualize how basically for any given tax revenue target, there's a menu of labor and consumption taxes that will reach that target, and basically that you can have either high consumption tax or high labor tax, but then the other one is always lower, or you can have a mixture of the two. So what this tells you is that there's not a whole lot to argue about when it comes to consumption versus labor income tax for this particular problem. Now, here's, now what we do, we went from borrowing yes to no borrowing. Now notice it really didn't have much impact on, let me see, did it have impact on anything? I think the horizontal and the vertical scales are the same. It really didn't do much. You seem to have a lot more points that are on the Pareto frontier. Now, by the way, let's look at these points over here. You might say, well, oh, we got these points. Now, my guess is that what needs to be done here is that one should do a sweep. You see, basically what happened is that the program started at some tax policy and then crawled up or went up to a point like this and then stopped. So these are local Pareto efficient points, but they're not globally. And so all one has to do to get rid of them is do a pass based comparing these points to these points, and then they would disappear. The marginal excess burden, by the way, these things are not going to be perfectly smooth. I was working on a problem like this once with a computer science person, and he visited me out here for a couple months. And then after a few weeks, I thought, well, I should have this coded up. And he said, well, yes, he said, but it isn't good enough. It isn't good enough. So I let him say that for about a week or so. And then I said, no, show me what you have. And he showed me some Pareto frontier between utility and revenue. And it was kind of a nice line, but it was scattered points and jagged. And I said, oh, that's beautiful. I said, that's fine. It's exactly, given the method he was using, that's exactly what I was expecting. It was not some smooth line. He was expecting it should be a smooth line. And so that's what he was going for. And of course, but then he showed me, I said, that's exactly what I'm looking for. And yes, because of the method you're using, you're not going to get a smooth line. Now, Philip here, now, by the way, that guy was doing Monte Carlo sampling and all sorts of stuff that doesn't exploit smoothness. But Philip here got smooth lines because he was exploiting smoothness. So then, anyway, so that's what you have to remember about these methods. You are doing local searches, and then you have to do global clean out. Perhaps a global clean out perhaps some of these points are leading to some of the extra points here. By the way, I doubt very much that I suspect these points will be wiped out. Also, now, by the way, the other thing is that I also think that in the future, go back to, let's say, this picture. Now, theory focuses on the frontier, the points that are absolutely on the frontier. Now, basically, I think we would be happy with our government if it came to be at least sort of within 1% of that frontier. And so okay, we're never going to be happy with the government, but whatever, we'd be happier if at least it got close to the frontier. So another concept here, it's very easy to implement, is to say, well, let's find the things that are epsilon Pareto efficient. And then we do that, and we might find that something which is never part of a Pareto optimal tax policy actually is epsilon Pareto optimal. And so let's not get all upset and fighting about it. So this is the kind of insight one can get. Now okay, so this is now a slightly different utility function. Gamma 0.5, eta equals 8, borrowing yes. And so it's roughly the same lessons here. Now, by the way, this is kind of a wacko thing, because there was one point which didn't get swept out that had minus 6,500 utility. And so the graph kind of got, the scaling got screwed up. Anyway, but that's why this looks so weird, because there's this one point that I'm sure it corresponds to a local Pareto efficient point. And then here we again have some locals, some ugliness. But the thing is that these are not ugly pictures. Some might think they are, but no, there's a lot of content in these pictures. The content in this one is that capital tax should be 0. You're not gaining anything. Whether it's Bob Hall, who has a family capital market to borrow when he's young, or whether it's Glenn Hubbard or me, who didn't have that. It turns out that the treatment of asset income should be the same. And so this is, of course, quite important when you talk about building political coalitions to pass tax reform. Basically, this will help tell you which policies are Pareto efficient for which groups, and then the coalition could be built around a set of policies which are good, are epsilon good for all the people in the coalition. So this is what can be done. Now, by the way, there's another, Carlos also looked at the problem where you had these 3 instruments, and it also had like a lump sum tax. That's a 4th dimension. And he did a brute force crawling kind of thing for that. And basically lump sum taxes don't do much of any good. But I mentioned that because Carlos, you see, when you have 4 dimensions, that's a lot of cases to compute. Now he was using ample, and then we were sending the ample jobs off to NEOS, Network Enabled Optimization Software, based at the University of Wisconsin. So I told him, look, okay, we're going to use NEOS, see how much we can use it. I said, so you're going to have to write up, let's say, like 100 job submissions, because you have I think a 4-hour time limit, and you can't do all of the millions of cases. So you're going to have to submit, I don't know, 100 jobs or so. Now, Carlos, having the right instinct, thinking that he has better things to do than writing 100 different ample submissions, he decided to use a tool that they have called Kestrel. And then he used some scripting software, and basically he rigged it up so that he told the computer the range of parameter values you wanted to look at and the increments between separate points, and then how many to send off in each job. And then this software he wrote automatically generated job submissions to NEOS. And when it was done, it automatically read the results and collected the results. And so one time I was talking about this, and I said, Carlos said he was busy doing all these jobs, but I'm sure I suspect he was really down at the beach. He was here at Hoover that time. And so I said that, just joking around, and then Carlos said, oh, well, yeah, I did go to the beach. So if you learn how to use these computer tools that allows you to automate things, you can spend time at the beach. While the computer somewhere else, in this case, Madison, Wisconsin, was crunching away. And so this is, it's a nice example of just embarrassingly parallelizability and having access to decent hardware power. You can do a lot. And now this is just the beginning. Also, Carlos also, for a while, we had access to Blue Waters, a supercomputer here in the US. And so we had coded things up to go in that direction, also using IP Opta as the solver. Anyway, so that now we'll have to find another supercomputer to do this. Now, what I want to do is find optimal labor and capital income taxes, and perhaps nonlinear ones. So you have a deduction, and then maybe a lower income, you have a small marginal rate, and higher income, you have a higher marginal rate, what we call a progressive system. Or the United States system is sort of a progressive regressive system. It's that initially marginal brackets go up, but then they go down for those of us that are in the top 2%, I guess. One reason is because after a certain amount of money, I don't know, about $110,000 annual income, we don't pay Social Security taxes. So our total income tax, basically total rate on income, drops. Okay. So now all of these problems, even with that kind of a partial, a progressive and then regressive tax system, solving the consumer's problem is trivial. It is trivial. It can be done very quickly. Even I've done that for static problems. I think I can also easily do it for dynamic problems, life cycle problems. And even when you have stochastic shocks to your labor income. So those are the kinds of problems I want to solve. And I want to solve optimal taxation where I have, where people are solving dynamic stochastic overlapping, dynamic stochastic life cycle problems. Now this sounds insane. And 30 years ago it was. Now, however, with the much improved optimization software, the much improved algorithms for doing dynamic programming, of which you've seen some, and with massive parallelism, I'm sure I could do it. It's a matter of getting the supercomputer time from somebody, as well as somebody to do the dirty coding for me. So these are the kinds of problems that can be done with multi-objective optimization. And so a lot of times optimization problems don't have smooth or concave objectives. They can be non-smooth and they can be ugly. They're hopefully piecewise smooth, at least. You have to be pretty perverse to come up with something that's not even piecewise smooth. And that's all. That's often good enough. But the constraints are going to not be smooth. Maybe be piecewise smooth. Not going to be convex, but that's fine. Because as with the tax problems, we can transform it into solving for the Pareto frontier. And that means because given the design vector, computing the utility payoff and the revenue payoff is very easy. And then if that's the case, then you can solve for the Pareto frontier, and then you line it up, and then you have some revenue constraint. You just figure out, just draw the line, and you solve the optimization problem. So solving a continuum of problems is straightforward, and it is easier and more reliable than solving a single one example of those. By the way, this also applies to principal agent problems. This isn't, basically optimal taxation is just a particular kind of principal agent problem. So this is available it can be used in many contexts. Now, and also the thing is that we also will use economies of scale, because like when you're solving the consumer's problem for a list of tax policies, you can do warm starts, which means that you take the solution from solving tau vector 1 and then use that as initial guess for a nearby tau vector. You could use hot starts, where now you use not only the solution from the previous tau as your initial guess, but you also bring over the approximate Hessian that you had for the end of the previous tau, and use that as an initial guess for Hessian and your new tau. Homotopy also trade. So the other thing here is that there's another example, solving 1,000 problems is probably only 10 times faster than solving one. Economies of scale. And I see numerical analysis is really just applied economics. You know, if you understand economies of scale, you'll do very well here. And so you can do this now. So this is all easy, you know, relative to the alternative. It's all obvious. You know what a Pareto frontier is, which you better by now. Now, computational mathematicians, like the story I told you, they don't like it because they want to solve things using their fancy problems with their KKT conditions or their relaxed KKT conditions, all sorts of stuff they love. So they don't like this. Economists won't like this for all the usual reasons. And that's why this has never been done in economics. All of which means that we can have a lot of fun doing this stuff. And that's what my intention is. Okay, so, somebody asked about what about global optimization? Now, I don't know when you asked that question. From the point of view of solving, okay, let's talk about the life cycle tax problem. In this problem where you had a consumption tax and a labor tax, the problem is a very nice concave, objective, convex constraints. And so there's no global, there's a unique optimum and there's no global optimization problem. If I had piecewise linear taxes on labor income, you might think that that would cause a global optimization problem, but it doesn't when you formulate it correctly. So basically, when it comes to solving the consumer's problem, I think you'd have to come up with a pretty perverse, strange tax system in order for standard methods to have problems with finding a global optimum. Now, Now, your point, yes. When I wrote the problem down as max of U of tau subject to R of tau, that has hideous global optimization problems. You never know if you're at the global optimum because of the bad feature, because the shape of R and U functions are so awful. Those people really have, people who solve that problem that way, they have a hideous a global optimization problem, which is why I don't like doing it that way. Now, whereas when you do the multi-objective thing, is that if basically in all the examples I can think of, solving the consumer's problem is easy given any tax policy, and then it's the Pareto dominance sweep that gives you the global optimum. So thanks for that question. Good. Yeah. No, very good question. Yeah. It's the problem. The global optimization problem is a problem why the conventional primal approach or even the dual approach is unreliable, is very limited in what it can do. And the multi-objective one gets through all that. Now, by the way, I've written up papers on optimal taxation. I tend to focus on what the steady state is because it's simpler and all that, and less problematic. But again, those papers were in the 80s and then 90s. I now want to go back to those and do dynamic versions numerically, which I think will allow me to examine the robustness of those conclusions. Conservatives kind of like me because of the paper I published in 1985. There's a working paper that circulated in 1989, 1990. Oh, conservatives are going to hate me when I start talking about that one, because this is a problem what we talk about when you have uncertainty, and basically it says that when there's a big negative shock to productivity, you tax capital. Oh, they're going to hate me because that's what we've been into. So, I make nobody happy. Everybody hates me, so that's fine. When you start doing these things numerically, you can examine all of these issues in a much more robust fashion. Okay, any other questions, comments?